Hi coding nomads, let's quickly continue from where we left. Now we are interested in building our first parameterized linear regression. This kind of linear regression is widely used everywhere. People are quite familiar with it actually. And sometimes it can be trickier to interpret the results, but it is still more straightforward than interpreting complicated machine learning models. With that being said, maybe I should highlight that if you have two different models, on one hand you have a sophisticated machine learning model. In this imaginary scenario, let's call it a convolutional neural network. And on the other hand, you have your simple linear regression, and they are performing similar in this scenario, okay? And when they are performing similar, then perhaps it can be a better idea to pick the linear regression model to present, especially to the business, because it will be perhaps easier to communicate. Okay, just keep this in mind for our future studies. As I mentioned in linear regression, we have this alpha and beta coefficients. What makes linear regression really powerful is that this beta coefficient, actually, our beta estimate, the slope coefficient, if you will, on the right hand side. And we will see in the future this x can be in functional forms, like it can be, for instance, it can be in cubic form in a linear regression. We will still call it a linear regression. It will not be a straight line, perhaps. It will be curved, right? But the idea is still the same. It is a linear regression because we have an intercept and slope coefficients. In this simple one, we have only one x, explanatory variable. Let's call it explanatory variable, maybe. And in this case, it is our distance to the city center, and our price is here as usual. Okay, and about its interpretation, yeah, sometimes it can be trickier if you claim causality, especially to the business. Claiming causality is something tough. You should list down your assumptions beforehand, okay, before claiming such thing. Even saying increasing, decreasing, or effect on something, they are really tricky interpretations. They can mislead you. They can mislead all of us. So when we are talking about this beta coefficient, we shouldn't forget it just represents the 1 unit change in our explanatory variable corresponding to price change. So you expect beta change in price when the distance changes by 1 unit. What I'm trying to tell here is that, for instance, if the distance changes from 1 to 2 kilometers, right? It changes from 1 to 2 kilometers, then you expect a beta change in price. That's how you should tell. In this imaginary line, let's say our beta coefficient is minus 30. It means 1 unit distance change corresponds to minus 30 euro change in price. That's all it is, okay? Quite straightforward, but when phrasing, we should be careful. That can because you should be better than cheap newspapers claiming causality, right? If you are studying this material. All right. Sometimes this functional form can have binary variables. Let's write another function here. So this is a new one, okay? Again, it has an alpha intercept, and it has again a beta coefficient. However, this time this x is a binary variable, so it takes two values, 1 or 0. It means when it takes 0, this part will be 0, and you will end up having intercept value only. How to use this is that let's have an imaginary line here, dividing our data into two groups, two categories. And I will call the first category, category 1. These are close by hotels. You are familiar with them now. And the second one is category number 2. They are the faraway hotels. Right? Maybe like this. Okay, let's take our pen. We will go into the code shortly, but let me discuss these first, and then we will implement these in our code. Okay, so in this binary variable concept, if we are a close by hotel, this x becomes 1. Let's talk about an intercept first. Let's say that our intercept came as 100. If it is a close by hotel and our beta estimate this time came as 30 plus 30, it's a close by hotel, and that's why it will take 1, and our prediction, if you will be 130. However, if it is not a close by hotel, this will be 0, and then this part will disappear, and then the prediction will be 100. How you read is that if it's a close by hotel, our price is 130 on average in this data. If it's a faraway hotel, then expected price is 100 on average in this data. That in this data part is important because there may be other experiments, other researchers, right? They maybe collect different prices, different hotels in Vienna again, but they will end up having a different slope for sure. So that's why we call this beta estimate. So we are estimating that this is our beta. We will talk more about this when we talk about confidence intervals later. Okay, so let me now talk about, okay, we are going into the code, but still I need to finish something here. So let me take a different color. There are some interesting hotels here. Let me mark them. So I am selecting these 3 hotels. And as you can see, they are like 30 euro in price, or dollar, I don't know. However, if we use our model for prediction, we will get a price like 100. There is a difference, right? So we call this residual. That's an important one. So let me write here residual. Okay. It's simply the difference between these two. In my small example, the residual is minus 70. I guess you can assume that this residual should be close to 0, right? For a great model. You want your residuals to be close to 0, I think. And that's actually how all the optimizations work under the hood. So they want to minimize these errors. This green line comes into picture, and the computer, the software, computes this line, if you will, and it is running an optimization under the hood, and it is minimizing the root mean squared error, the RMSE. I will write it here. This is going to be an important metric in your data analysis journey, RMSE. This is an accuracy metric, and in regression studies, this is the most popular one, root mean squared error. In root mean squared error, we just don't take these absolute numbers as penalty. We transform them a little, we make them a little smarter, if you will. We will come to that formula later for RMSE. However, that's how the computer fits this line. It is minimizing the distances from all these hotels. So let me try to draw it here. That's why sometimes this is called ordinary least squared. Ordinary least squared means it is minimizing RMSE actually, or mean squared error. There are distances, right, to the line. So this procedure, algorithmic procedure, is minimizing the average distance, okay, and it is finding this average line or average curve based on this optimization. And the penalty metric for minimizing these average distances is RMSE, the root mean squared error. We will talk a lot about RMSE. I will not dive deep into that at the moment, because at the moment I want to implement this into our Jupyter notebook again. Okay, how to do that? I'm going to use Statsmodels library, and later we will use also scikit-learn library and compare these two libraries. But I want to start with Statsmodels because we are talking about exploratory data analysis here. We are interested in finding coefficients and interpreting them to understand the variation in our target variable. And if that's your goal, then Statsmodels can give you better summary statistics and summary outputs for your regression models. If you're later, when you get more experience, and if what you care about is only to get the predictions as fast as possible, then scikit-learn is the right way. You should know the differences between them, otherwise they will do pretty much the same work for you. Anyway, let's check what we have here. So yeah, we had this one, the regression, non-parameterized regression. We were checking the close and far away hotels. Let me copy this here as a markdown. This is now code. Let me change it to markdown and change the name to linear regression. Cool. Statsmodels, yes, just go to the documentation and read through what they are doing here. This documentation is quite dry. They don't talk much about why they are using something, when they are using something. It is just talking about implementation of the functions, which is pretty much important to you actually. And there are nice code snippets that you can use here. I use this all the time, this documentation, whenever I need to do some exploratory data analysis. First things first, let's import our Statsmodels library as SM. So we will be calling our Statsmodels functions using this SM notation. I hope I have this library in my environment. It is still running. Yeah, I have it. Thank you. So let's see what they are doing here. First, it is loading a data from somewhere, probably within the library. They have some sample data sets. We don't need this one because we already have our data, right? In here, it is adding the constant. Adding constant means they want a model with intercept, just like us. So let's first define our x variable within this data. But I forgot how the data looked like actually. Let me check. Yeah, we still have this with a lot of columns. I want to select only the columns I need, okay? Let's call it df number 2. From df, give me only distance and price, because that's going to be our model. And it should look all right, hopefully. Right, here they are. I will jump right into fitting a model, okay? My x variable is df2 distance. This is my explanatory variable, or right-hand side variable, or independent variable, right? And df2 is our price. df2, select my price, I mean y variable, okay. Now we have selected them. After we define our x and y, yeah, and here we are adding the constant. Let's use this function. Oops. let's add our constant. Our constant will be for our x, and we are going to pass this x and find this. This will mark actually. This will mark that, how to say, I need this constant, meaning intercept. I am commanding it to produce a constant for me. Let me show you what I mean. If I run x here quickly, so see constant 1. If we don't have this const column, it will be a regression without intercept. It is totally doable technically. If you want to try that, yeah, go ahead and try it. However, in this one, I need my constant. Okay, let me delete this. I just wanted to show that it adds this constant to our set. Let's fit it. Fit and see. So this is going to be our model, right? It is simply using the sm.ols, meaning ordinary least squared, meaning linear regression. They are synonyms. So my model should be sm with dot notation. If you hit tab, you will open up. By the way, let me make this bigger. I hope this is big enough. Cool. So still we have this dot notation here that we can use, and these are the functions I can use in Statsmodels. Here I am looking for OLS to fit ordinary least squared linear regression, and I need to pass my x and y. That's it. And then fit. Fit what? Basically, we are fitting our curve, right, to the data. That's why. First, we are defining our data, and then we are passing our data to ordinary least squared object, and then finally fitting it. And when I run this, it is running that optimization that I mentioned in the background. Ordinary least squared procedure is running under the hood and gives you the output, and it is optimizing for that RMSE that I talked about. It is finding the average curve or average line that is closer to all the points on average. So this is the model object now. It was quite fast, right? Because this is just a small data for learning purposes. Okay, now this model object has different functions and properties. You can print and observe many different properties and functions here, and go ahead and read the documentation for that for sure. What I need is reading a summary. I just want to read the output of this modeling study. Okay, nice. We got our first error message, and I don't know what that is. Okay, probably I let's check what they say here. Yes, that data is actually the y variable. Okay, y, x as exploratory variable, y as target variable. I think the locations were supposed to be different when we are passing. Cool. Now it's, yeah, that was the case. So the positional argument. So y first, x next. All right. So this is our model summary. It looks really complex and busy. There are lots of things to read here, but if I were you, I would just focus on to the middle section you see here. Okay. Avoid the others for the time being. We will read the others also later, but for the time being, let's just read this middle section. That is the important part. What do we have here? We have the constant. This is the intercept that we were drawing in our graphic. And this is our explanatory variable, the distance. This is our coefficient estimates, which means it is crossing the y-axis from 151. Let me try to find it here. See, it found a line like this, just like I was drawing. My drawing crosses the y-axis from like 145, because I was just guessing, right? However, the real one, the optimized one, crosses from 151. That's our intercept. And the second one, of course, our distance, our slope, this beta. Okay. And remember how we were interpreting, right? So the price changes minus 12 for 1 unit change in distance. So if it becomes 2, if it was 1 and it changes to 2, the price changes minus 12. That's it. And we have a few more columns here. I will not go into very much detail here because we will have a separate section for that. But maybe I should just say that this is the p-value, and this is smaller the better. Generally, if this is smaller than 5%, it means it is statistically significant. That means finding these coefficients by pure chance is really difficult. So probability of finding these coefficients by pure chance is really low, and it is this probability you see here, and it's extremely low, which is a good sign that it means these coefficients are useful, or we think they are useful for the time being, right? And this is good that it is really small. And t-values, yeah, t-values are just another way of looking at to the same thing. Actually, this is for the standard normal, the distance by standard deviation. We will cover that later, I guess, or just pick up a book and read about the t-values. So this part is about the confidence intervals. This is again another way of saying the same thing, like these coefficients are useful. Later we will have a section about confidence intervals and we will do examples about it. However, here I should say that the important thing is that the 0 should not be a part of this interval. Here the 25 and 975, and this is the interval of 95% interval, and it changes from 138 to 163, and this one changes from minus 17 to 6%. So 95% of the time this is the range you will find in different samples. Another way to put that is, if there were 100 parallel universes, in 95 of them you would find this coefficient in this range from minus 17 to minus 6. And it's a nice property that 0 is not a part of this range, because if 0 was a part of this range, this coefficient might as well be 0, and it means it might as well be useless. However, we don't see 0 here in this range of confidence interval, which is again a good sign. Okay, we will do more practices about this later. Nice. Now that we have our model, we did some beginner level interpretation here. We didn't touch some important information here, like the R squared, but we will come to that later. No worries. Now, how do we do prediction on top of this model object? First, I want to show that. So predictions will be equal to model dot, I hit tab for auto-completion. If I call the predict function on top of x, then I should have my predictions array, which might look like this. Because I have 427 hotels in this data, I have this many predictions, which is normal, I guess. It starts with 118 and then it ends with 142. Good. And if you remember, my DF 2 was something like this. Now I want to create a new column here with my predictions, okay? Let's do that. df2 with log notation. I want all the rows and create a new column called pred. And this pred should simply be my predictions. If these would be in different lengths, then this code would not work. Anyway, it would. Let's run it first. Maybe it will fail anyway. Cool. Let's now just see quickly, by avoiding that warning message, what we have there. We are looking at our predictions next to our price. And if you remember, we had this concept of residuals. And in this graph, I marked the orange ones. And if you think about it, I guess these are best deals. These hotels are close to city center and really cheaper than we expect on average in this data, right? Okay, let's get our residuals to our data frame as well. So how to create residuals? Again, we will use this log method. I need all my rows. This time I need to create a new column called residual, and it will be simply the difference between price. Select your price column and minus your pred. Let's see what this gives us. df2 head. See, these are our residuals, and let's check something. I want to see maybe a little graphically. Let's create a let's try to create a plot. Okay, so I want my df2 and select my price and pred, and then I want to plot them. Let's first run this and then we will make it better. It looks a little small. Let's make it a little bigger. I guess this fixed size could be used here if I remember right, but we will see. Okay. Yeah, fixed size is there. So the orange line is the model output, the model's predictions, and the blue ones are the real prices. That's why our residuals are big. Okay. This is one way of looking at your residuals. Again, we can plot the price, distance, plot scatter. Yeah. Oh, scatter takes X and Y, of course. Distance, let's say price. Will it accept in string format? Let's see. Yeah, it accepts. Okay, so we fitted a line here to the hotels with price, I guess, smaller than 600. I don't remember if we did this filtering here, but the line was fitted here somewhere after we processed the data, and then we found some prediction outputs using the Statsmodels library, and then we checked our residuals. We interpreted our results. That was important. We did not claim causality or effect. We were just comparing the averages, changing average prices based on distance. And that's it. We were simply able to implement what we were drawing here. We just didn't touch the binary variable yet, but we will do it in the next one. Okay? So until next time, keep practicing. Bye.
Hey everyone, thanks for watching. If you enjoyed this video, please let us know by liking and subscribing. If there's another topic that you'd like to learn more about, leave us a comment. We would love to hear from you. And if you want to become a coding pro, visit our website at codingnomads.co. See you next time.